Hello, today I am going to present our project for Mechatronic 1 titled The Estimation of the State of Health in Lithium-ion Batteries for Electric and Hybrid Vehicles. This work aims to contribute to smarter battery management systems, ultimately supporting the broader adoption of sustainable transportation. Let's begin. To guide you through our presentation today, here is our table of contents. We will begin by defining the state of health, or SOH, and explaining its critical importance. Next, we will cover the essential pre-processing steps we use to prepare our raw battery data. Following that, we will detail our modeling approach starting with the deep neural network architecture and then the LSTM neural network. Finally, we will bring it all together to present our results and a concluding summary. In this slide, we begin by looking at the critical global context driving our project. The world is facing a dual crisis: the decreasing availability of fossil fuels and the growing environmental concerns associated with them. This has turned the development of clean, sustainable energy into a global necessity, creating an urgent need for advancements in energy storage technologies. This is precisely why lithium-ion batteries are a key solution. Their advantages like high energy density, lightweight, and long cycle life have made them indispensable across various industries, especially in electric vehicles, where they play a vital role in reducing environmental pollution. However, these batteries are not without their challenges. The continuous charging and discharging cycles cause the erosion of active materials and depletion of lithium. This degradation leads to a reduction in overall performance and decreased driving range for EVs, and most alarmingly, it can create serious safety hazards like fires and explosions. This is where predicting the state of health, or SOH, becomes an absolute necessity. Accurate SOH estimation is crucial for extending battery life, reducing cost, enabling early problem detection, and preventing sudden failures. Therefore, our project focuses on this vital task. We will define SOH, detail our pre-processing steps, and then explore and compare the use of two powerful AI models: deep neural networks and LSTM neural networks, ultimately presenting our results. As I mentioned earlier, this work is a critical step towards smarter energy storage and a more sustainable future. Let's talk about pre-processing steps. To ensure the highest levels of accuracy and robustness in our predictive models for battery health, we cannot simply use the raw, uncleaned data directly from the sensors. Raw data is often messy and unreliable. Therefore, we implement a rigorous three-stage pre-processing pipeline to transform this data into a clean, reliable foundation for analysis. The first critical stage is noise detection. During battery cycling, sensor readings for voltage, current, and temperature can be contaminated by signal interference, electromagnetic noise, or simple measurement errors. If left unaddressed, this noise can severely mislead our AI models. Our process involves applying statistical filters and signal processing techniques to identify and smooth out these anomalous spikes and erratic points, ensuring we are working with a clean signal that truly represents the battery's behavior. Once the signal is clean, we move to the second stage, handling missing values. It is common in time series data to have gaps where data points were not recorded due to sensor glitches or transmission errors. You cannot just ignore these gaps. To solve this, we employ intelligent imputation methods. Rather than using a simple potential biased average, we use techniques like linear interpolation or k-nearest neighbors to estimate the missing values based on the surrounding data trends. This careful approach fills the gaps in a way that preserves the underlying patterns and dynamics of the battery's performance without introducing artificial bias. The third and final preparatory stage is normalization, also known as scaling. Our features like voltage and current are measured on different scales. A voltage value might be around 4 volts, while a temperature reading is 30 degrees Celsius. If we feed these vastly different numbers directly into the model, the larger scale features could disproportionately dominate the learning process. To prevent this, we scale all features to a common consistent rate, typically between 0 and 1. This crucial step puts all parameters on a level playing field, allowing the model to learn the true relationships and patterns effectively, rather than being skewed by the arbitrary units of measurements. This end-to-end pre-processing pipeline comprising noise removal, missing data imputation, and feature scaling is not just a technical formality. It is a fundamental and critical process that transforms volatile, real-world data into a structured, clean, and reliable dataset. This directly enables the high performance and transversal results we achieve from our subsequent deep learning models. In this slide, to predict critical values like a battery's state of health or SOH, we represent the main structure of deep neural networks or DNNs. The network structure begins with an input layer that receives raw sensor data like voltage, current, and temperature. This is followed by multiple hidden layers which work together to extract complex, nonlinear features from this data. Finally, an output layer produces the prediction for SOH. The processing in each layer involves two key steps. First, multiplying the inputs by weights and adding a bias expressed as y equals w times x plus b. Then an activation function like ReLU is applied to introduce nonlinearity. With these deep processing capabilities, DNNs are highly suitable for identifying the intricate patterns in battery data and for making accurate predictions across various operating conditions. When we talk about predicting a battery's state of health, we are dealing with classic time series data. The capacity of a battery in cycle 100 depends heavily on what happened in cycles 50, 75, and 99. Traditional models struggle to remember these long-term relationships. This is where long short-term memory networks or LSTMs excel. There are two key features as listed here are what makes them so powerful for our task. First, they are specifically designed for learning long-term dependencies in sequential data like ours. Think of it like remembering the beginning of a sentence to understand its end. For a battery, it's about connecting subtle early signs of degradation to a much later loss in capacity. Second, and this is the technical genius behind it, they solve the vanishing gradient problem. In simple terms, as a regular neural network tries to learn from earlier data points in a long sequence. The instructional signal it uses to adjust its weights gets weaker and weaker until it vanishes. It essentially forgets how the early data was important. The LSTM's unique architecture prevents this, allowing it to learn effectively even from sequences hundreds of cycles long. So, how does it achieve this? Through an ingenious gate structure that acts like a meticulous manager of a memory cell. Let's break down each gate. The forget gate is the first decision point. It looks at the new input and the previous hidden state and decides what information from the long-term memory is no longer relevant and should be deleted. In our context, it might decide to forget a temporary temperature spike that was just sensor noise. Next, the input gate decides what new information is valuable enough to be stored in the long-term memory. It works in tandem with the candidate cell state to update the memory. For battery, this could be the crucial moment it identifies a persistent saddle drop in voltage that signifies the start of degradation. Finally, the output gate controls what information from the updated memory cell is sent out as a hidden state to the next layer. This output is also the model's prediction. It filters the most relevant information for the next step. It might output the probability that the battery's health has decreased based on all the patterns it has remembered and forgotten. In essence, as this animation shows, an LSTM uses this gate mechanism to carefully map information over time. It's not just a blind passage of data, it's a deliberate process of remembering, forgetting, and updating. This allows it to remember past patterns with long-term dependencies, much like how you remember the theme of a melody from the first few notes. This ability to contextually manage memory over long sequences is precisely why we choose LSTM networks to model the complex, time-based degradation of lithium-ion batteries. It allows us to not just see data points, but to understand the stories they tell over time. Now, let's examine the core of our project, the results of our state of health predictions and how our models performed. As the slides outlines, our process began by splitting our dataset into training data, used to teach our models to complex patterns of battery degradation, and test data used to evaluate their real-world predictive accuracy on unseen information. We then applied our pre-processing steps and ran this data through our two architectures, the deep neural network and the LSTM neural network. The results are visualized on this graph. The x-axis shows the battery cycle count from 20 to 120 cycles, representing real-world usage over time. The y-axis represents the state of health, starting from a health 0.90 or 90% and degrading down. You can see the actual measured SOH of our test data, which shows the true nonlinear path of degradation. Plotted against this are the DNN predictions and the LSTM prediction. The key takeaway is how closely each model's prediction line follows the actual test data. We can observe which model more accurately captures the rate of decay, especially at critical points. The LSTM, with its innate ability to handle time-series dependencies, typically demonstrates a superior performance in tracking the long-term trajectory of health loss, resulting in a lower prediction error. This visual comparison allows us to quantitatively validate the effectiveness of our chosen AI approach in solving this critical problem. In conclusion, our project has successfully demonstrated a data-driven approach to a pressing challenge in the transition to electric mobility. By leveraging advanced AI techniques like deep neural networks and LSTMs, we have built models capable of accurately predicting battery state of health. This work is more than an academic exercise. It is a step towards building smarter, safer, and more reliable battery management systems that can extend battery life, elevate user anxiety, and ultimately support the sustainable energy future we are all working towards. Thank you for your time and attention. I'm now open to any questions.